Okay, here we go back to the local analysis. And so the first topics now is a topic which is extremely popular for students. And the title is the Lupital Theorems. So there are two important things to say about the Lupital theorems. They are very popular among students. They are not so popular among professors, but I think in this case students are right because they are very, very, very useful, as we will see in the theory. But I have to say two important caveat. You know what is a caveat? Caveat is be careful. Two important caveat. It's a Latin word which is used as warnings. First important caveat. The L'Hôpital does not say, does not establish that a certain limit of ratio of two functions is equal to the limit of the derivatives. In the sense, does not says that. It is not true. It says that this is true provided that some hypotheses, there are hypotheses to be fulfilled. This is quite obvious because it is a theorem, so it has hypotheses. But in the case of the L'Hôpital, the hypotheses tend to be forgotten very easily by students, okay? So always remember that there is the hypothesis, and moreover, or probably more relevant, the logic of the theorem is another one. Is not this, the equivalence of these two limits. First. Second, the L'Hôpital theorem are not by the L'Hôpital. Okay, many theorems have a name of someone who really did not contribute to the theorem, okay? But the history of the theorems by the L'Hôpital is particular because the L'Hôpital wanted to occupy a place in the history of science. So he asked Jacob Bernoulli, so they are due to Jacob Bernoulli. Asked him whether in his header, Mr. Jacob Bernoulli, who was very strong but was quite poor, had a theorem to sell to him. So Bernoulli sold certain theorems that he believed not to be so important. Then the L'Hôpital became famous because the theorems are in fact very important, but after the death of the L'Hôpital, Bernoulli showed the letters and so the proofs that he was the author of the theorem, even though he had sworn to Bernoulli that he would never say the truth. And so it is a nice story to be read in the books of history of mathematics. Okay, but the important thing that you have to know is this. Of course, this is just a warning, and I will explain you in a better way. But okay, I tell you immediately, yes, why not? But what is the true logic of the L'Hôpital theorems. This is the question. The question is the following. First, you have to compute the limit of the ratio of two functions, f and g. Limit for x tends to some x bar, okay? This is to be computed. And, very important, first important hypothesis, both fg go to 0 when x go to x bar, or fg go to plus infinity or minus infinity as x goes to x bar. So it is very important that the ratio here is an indeterminacy case. Otherwise, this is not true. First. So this is... And the third point, very important, there exists the limit of the ratio of the derivatives. Then the equality here, against which I warned you at the beginning of this lecture, then this equality holds. Okay? This is the logic. And before seeing that, we see a simpler version for a simple case of the Lupital theorem. So this is the theorem of the Lupital, let me say. First theorem by the Lupital. So let E be an interval. Fg from E to R. Fg are differentiable at a certain point at x bar in E. So in particular, x bar is an internal point. So they are continuous in x bar, and we can say that f of x bar is equal to g of x bar is equal to 0. So here we are not talking about really the case of indeterminacy. Here we have the value at x bar, which is 0. However, it is also the limit of the two functions because they are continuous at x bar. And g prime of x bar is not 0, then the limit for x tending to x bar of f of x divided by g of x is equal to f prime of x bar divided by g prime of x bar. Proof is really very simple, one-line proof. Let us consider the ratio of f divided by g. And consider the expansion of the two functions due to the definition of the derivative. F is differentiable in x bar, so this is equal to f of x bar plus f prime of x bar times x minus x bar plus little o of x minus x bar divided by g of x bar plus g prime of x bar times x minus x bar plus little o of x minus x bar for x towards x bar. Okay, but now f of x bar is equal to 0 by hypothesis, also g of x bar, and using the negligibility principle, you have that this tends, sorry, not equal it, limit tends to f prime of x bar divided by g prime of x bar as x goes to x bar. End of the proof. So this is extremely easy. And first example, we have f of x is equal to sine of x, g of x is equal to x, and x bar is equal to 0. And g prime of x is equal to 1, which is different from 0. So the limit for x going to 0 of f of x divided by g of x is equal to the limit for x going to 0 of f, is equal not to the limit, but is equal to f prime of x bar divided by g prime of x bar. So this is equal to the cosine of x bar, which is 0, divided by 1, and this is 1. Okay, very simple case. You can think of many other cases like that. So this is useful in order to introduce the second theorem by the Lupital, which is the following. That says that we have fg from AB to R. AB is an open interval. This time both functions have to be differentiable in all the interval AB except possibly the point x bar, where x bar is a point in AB, and continuous in AB. Moreover, in this theorem we have the usual, as in the previous theorem, condition f of x bar is equal to g of x bar is equal to 0, and the limit of the ratio between the derivatives, f prime of x bar divided by g prime of x, sorry, not x bar, f prime of x divided by g prime of x is equal to the same L, is equal to L in R bar. So there exists this limit. This is the important hypothesis. Then the limit for x going to x bar of f divided by g is equal to L. So now you see here the logic that I anticipated about the Lupital theorem. So the point is that you must have that the limit here, this limit, is an indeterminacy case. 0 over 0 in this case. And then you must know that this limit exists, and then you are authorized to go back from the limit of the ratio of the derivatives back to the limit of the ratio of the functions. So, proof. So, f of x divided by g of x equals f of x minus 0, and 0 is f of x bar, and here g of x minus g of x bar. Remember the hypothesis that says that these two quantities are 0. Now, why did I write 0 as f of x bar and as g of x bar? Because here we can apply Cauchy theorem. And now you see that Cauchy theorem is important by itself, not only because of its corollary, well known as Lagrange theorem. So, Cauchy says that there exists a C between x and x bar, but we don't know whether x bar is larger than x bar, than x. So here union with x bar x, okay, such that the ratio of f of x divided by g of x, so this quantity here, is equal to the ratio between the derivatives. So now it is done. Here we have the connection between the ratios, but you see that in order to have this connection, we have to exploit that f of x bar and g of x bar are 0. Okay. Now, we have that c minus x bar, because of this, is smaller in absolute value than x minus x bar. So since c is between x and x bar, or x and bar and x, depending on what is larger, then the distance between c and x bar is less than the distance between x and x bar. So the situation is, for instance, this: x bar, and c is here. Okay. Then, as usual, so we let x go to x bar, and we have, by double comparison, c going to x bar. So when we compute the limit for x going to x bar of f of x divided by g of x, this is equal to the limit for x going to x bar of f prime of c, g prime of c. But c goes to x bar. So this is equal to the limit by change of variable for x going to x bar of f prime of x divided by g prime of x. And this is equal to L. So since this limit, I write here to be more precise, since the last limit exists, then this guy here exists, then the second last limit exists too, and it equals L. Okay? This is the end. More important than the proof, the important fact of this proof that you use Cauchy theorem. So you see Cauchy theorem, and then you see. So another example, important example, is the following. Limit for x going to 0 of 1 minus cosine of x divided by x squared. Okay? So, of course, this goes to 0 as x goes to 0, the numerator, and also the denominator. So we are in the case of the second theorem. And look at the derivative. You have 1 minus cosine of x prime is equal to sine of x. X squared prime is equal to 2x. Now check the limit of f prime divided by g prime for x going to 0. This is the limit. The limit of the ratio of the derivatives is the limit sine of x divided by 2x, and this is 1/2. Then, by the second, the Lupital theorem, one has that the limit for x going to 0 of 1 minus cosine of x divided x squared is equal to 1/2. Of course, you already knew this result, but now you knew it with another method that can be useful to know. Now we go to the third theorem of the L'Hopital. This is the L'Hopital 3. This is the case in which x bar is equal to plus infinity. Okay, and here we have f g from a to plus infinity to r, such that f g go to 0 as x go to plus infinity, and there exists the limit for x go to plus infinity of the ratio between f prime and g prime, and this value is equal to L, which is in r bar, so it can be also plus infinity or minus infinity. Then the limit of the ratio of f and g exists too, and this is equal to L. The proof is extremely simple. Here we have the limit for x going to plus infinity of f of x divided by g of x, and now since x goes to plus infinity, then you perform this change of variable. Y is equal to 1 over x, and y tends to 0 from the left. So this is limit equal to the limit for y, which tends from 0 from the left, of f 1 over y divided by g 1 over y. So, of course, f of 0 is equal to 0, is equal to g of 0. So let us check the ratio of the derivative. This is the ratio. And of course, here you have to differentiate first the external function, then multiply by the derivative of 1 over y, and here you have g prime 1 over y minus 1 over y squared, and so what you learn here is that the limit for y going to 0 from the left of the derivative with respect to the variable y of f 1 over y. Notice that here, where we have two variables, the Leibniz notation can be interesting. This is equal to the limit for y going to 0 from the left of f prime 1 over y divided by g prime 1 over y. And this is reversing the change of variables, so introducing again the x. This is equal to the limit for x going to plus infinity of f prime of x divided by g prime of x, and this is equal to L. So we conclude that the limit of this ratio of derivatives exists, and then we can apply the L'Hopital case 3. Sorry, yeah, by the L'Hopital 2. This is the L'Hopital 3. We have that the limit L is equal to the limit for y going to 0 plus of the ratio of the two functions. And again, by change of variable, that restores the variable x, you end up with the limit for x going to plus infinity of f of x divided by g of x. This is the third theorem of the L'Hopital, and then we gave the last theorem of the L'Hopital, which is the fourth. So theorem, this is the theorem again due to the L'Hopital. This is the fourth theorem that it concerns the case infinity over infinity. You have f and g from E to R. E is an interval, and again x bar is in E, an internal point of the interval, not the extremes. And then we have fg go to plus infinity or minus infinity, this is not important, as x goes to x bar. And moreover, there exists the limit for x going to x bar of f prime of x divided by g prime of x. And this is L in R bar. Then the limit of the ratio of the function is equal to L. Okay? So it is exactly the same theorem, but with a different point. The point is that now the indeterminacy case is not 0 over 0, but it is infinity over infinity. What is the proof? And now, surprise, the proof is omitted. Why? Because if you want to do it properly, precisely, it takes many time and many pages, and basically does not deserve it. What is important for these theorems is that you learn very well the logic. So I want to insist a bit on logic and on examples, but I will do it in the next video.